Welcome all. So today we will be solving a problem from TIFR 2020, the problem number 70. Okay. So as you can see, the problem, the way it's been stated, it's quite obvious that it is a minimal polynomial problem. Why? So there are some uh, certain hints in this problem that you need to be kind of sure if you want to understand how you want to solve this problem. So first thing is that there is a polynomial of linear transformations. Right? So this is a polynomial regarding t, and it has degree 3. All right. So where I have t from R3 to R3. This is one hint. Another hint is this, that for every such linear transformation, that means if I take a linear transformation whose characteristic polynomial is also this, then what can we say about the diagonalizability or the invertibility of the matrix? All right. So there are certain things that you need to know to solve this problem. The first thing is that if you take any vector space of dimension n and you take any linear transformation t from that dimension n vector space to the dimension of m vector space, then with the choice of basis, let's say beta v and beta w. So these are the basis set of basis vectors of v and w. So there is an equivalence. That means the linear transformation t can always be represented as an m cross n matrix. So m cross n matrix. All right. So over whichever over the field on which these v and w are both defined. So this is the first step. There is an equivalence. It's practically, so let me write it down. Practically, a collection of all linear transformations from v to w of finite dimensional n and m. So this is equivalent to taking all such matrices, m cross n matrices of the same field, the same field. Okay, so it's practically, if v is a vector space over f, w is a vector space over f, then this set is practically equivalent to m mn f. So this is the first thing. The second thing you need to understand to solve this problem is the definition of a minimal polynomial. So in short, a minimal polynomial is the least degree polynomial that divides the characteristic polynomial and which has the matrix as its root. All right. So there are two things to understand, is that the linear minimal polynomial is the least degree polynomial that divides the characteristic polynomial. Secondly, if m of x is the minimal polynomial, is the minimal polynomial, this implies m of a is 0. So this second point actually takes us to one very good observation, is that all the eigenvalues are there. So what do I mean by all the eigenvalues are there? It means that if you take a minimal polynomial, then it will consist of all the eigenvalues of the matrix. It might not occur as many times as it's occurring as a root of the characteristic polynomial, but all the eigenvalues will occur in the minimal polynomial. And the last but not least is this, that when can we say a matrix is diagonalizable. So a matrix is diagonalizable if and only if the algebraic multiplicity of each eigenvalue is same as the geometric multiplicity of the same eigenvalue. So we will write it like this: Am of lambda has to be equals to Gm of lambda for each fixed lambda. So what is the geometric multiplicity? What is the geometric multiplicity of an eigenvalue? The geometric multiplicity of an eigenvalue is this. So let's say you take En in M in F, all right, and let's say lambda is an eigenvalue of A. Okay, so what is the geometric multiplicity of lambda? So the geometric multiplicity of lambda is N minus rank of A minus lambda I. So precisely the nullity of A minus lambda I. So that's the geometric multiplicity of an eigenvalue. What is algebraic multiplicity? Algebraic multiplicity is precisely the number of times the eigenvalue is occurring in the characteristic as the characteristic polynomial's root. So algebraic multiplicity is something like this. So let's just say if you have the characteristic polynomial like this, lambda minus 1 whole cube into lambda minus 2 like this. So then the eigenvalue, if this is 0, then the eigenvalue 1 has algebraic multiplicity 3, whereas the eigenvalue 2 have algebraic multiplicity 1. It's basically number of times it's occurring as its root. All right. So this is an if and only if condition for diagonalizability. Always remember that. So this is if and only if for diagonalizability. So this is an if and only if condition for diagonalizability, that algebraic multiplicity will be equal to the geometric multiplicity. Now let us look for the question. So what it's saying, that if I have this equals to 0, then which of the following is true? So one of the properties of minimal polynomial is this, that if P of E is 0, then mx divides P of x. So where I am consistent with my minimal polynomials notation. So that means if you take any polynomial of the variable matrix E such that is 0, then that polynomial will itself be divisible by the minimal polynomial. Okay. So now if you look at this, that the given equation is t cube, just a second, t cube minus t square minus t plus I, t cube minus t square minus t plus I. All right. So they are saying that for every such t, if this is 0, then what happens? So for our convenience, what I can take is that I can take x cube minus x square minus x plus 1 as the characteristic polynomial of P. All right, because characteristic polynomial is also a degree 3 polynomial which has to satisfy this equation, right? So I can choose my t to be, I can choose my t in such a way that this becomes my characteristic polynomial. It might, I mean, like, it will help because it will reduce our computation. So if this is the characteristic polynomial, so then this you can actually write it like, you can actually produce, you can factorize it. Okay. So if you factorize it, then you will see that you get it x minus 1 whole square into x plus 1. Okay, so that's factorizing. So if this is the characteristic polynomial of P, then the minimal polynomial has to be the least degree polynomial that divides the characteristic polynomial as well as contains all of its eigenvalues. So the first of all, the eigenvalues are 1, -1 in their own algebraic multiplicity counted, right? So the distinct eigenvalues are 1 and -1 if I take this equation to be my characteristic polynomial. So if you're wondering that can I take it, yes you can just take this matrix. You will see that the characteristic polynomial is precisely this one. So if you take this matrix, then the characteristic polynomial is precisely this one. So now if we are talking about the characteristic polynomial having this form, what will be the minimal polynomials? So the minimal polynomial will be of this form, either x minus 1 whole square into x plus 1, this is one possibility, or x minus 1 into x plus 1. So these are the two possibilities for the minimal polynomial. All right. Now, the algebraic multiplicity equals to geometric multiplicity. That follows from this method is that A is diagonalizable if and only if the minimal polynomial splits in linear factors. All right. So this is an if and only if condition for the diagonalizability, which you can basically derive from this equivalent condition that the algebraic multiplicity is same as the geometric multiplicity. Okay. So now from here, as you can see that since the eigenvalues are 1 or -1, some options can be readily eliminated. All right. So as of now, we can safely say that this is eliminated. All right, but not necessarily invertible, because even if this is not the characteristic polynomial, the only root it has is either 1 or -1. So there is no zero. I mean, there is no zero in the root. Hence, there is a possibility that it will have an eigenvalue as 0, right? So that's there. So we have an invertible matrix, but the problem is here now that if the minimal polynomial was this, in some way, if you knew about our choice of linear transformation, from there we could have pinpointed that what is the minimal polynomial. But since it is not, if the minimal polynomial is of this form, x minus 1 whole square into x plus 1, then the matrix will not be diagonalizable. The linear operator equivalently will not be diagonalizable, because this is not splitting into let's say distinct linear factors. It should be mentioned it's in distinct linear factors. Distinct is important. So if I write it down like this, remark, the most important remark is A belongs to M and F is diagonalizable if and only if the minimal polynomial splits into distinct linear factors. Right. So this is the remark, all right? It can be shown from the algebraic multiplicity equals to geometric multiplicity. Hence, in this given problem, if there might be a possibility that the linear transformation that we are taking, it has the minimal polynomial as x minus 1 whole square into x plus 1 itself. So this might be the linear polynomial, but then it is not splitting into distinct linear factors. Thus, it need not be necessarily diagonalizable. All right. So this is one way to prove it. Other way is directly give a counter example. So the counter example, so this is the other way around. So if you look at this matrix 1, 1, 0, 1, 0, 0, 0, minus 1, 0. If you look at this matrix, then the characteristic polynomial, as I have said before, is precisely the polynomial that has been given to us. All right. So if we compute the minimal polynomial of this, or rather if you want to compute the, so let's say what is the characteristic polynomial? It is lambda minus 1 whole square into lambda plus 1. So this is the characteristic polynomial of A. Let's call it A. Okay. So then 1 is an eigenvalue of algebraic multiplicity 1. 2 minus 1 is an eigenvalue with algebraic multiplicity 1. Right. So just take E minus lambda I. So, but taking lambda equals to 1. So if you take this, then this matrix will look like this: 0, 1, 0, 0, 0, 0, 0, 0, minus 2. All right. So whenever you have 0, 1, 0, 0, 0, 0, 0, 0, minus 2, this has rank. All right. Hence, this has nullity 1. So the moment this has nullity 1, it shows that even though the algebraic multiplicity is of 2, the geometric multiplicity is 1. Thus, it is not diagonalizable. So we had a matrix that had the same characteristic polynomial but not diagonalizable. So thus, in this problem, the solution to this problem is P is invertible but not necessarily diagonalizable. Okay. So that's all for today. We will meet again with another problem from TIFR. Thank you for joining us.